Alright, good afternoon, and just going to go through one of my favorite things is actually using math in ways that people don't normally think about, and making it fun, using ordinary everyday objects to make math that much more interesting. You're probably rolling your eyes saying, I can't stand math. If you happen to like math, fantastic, that's a great thing. I've always liked math. I see math in everything. But I'm going to show you this one little trick, and hopefully it'll kind of get you to be inspired about what else you can find with math. So it is with my napkin, and in this case it's actually a simple paper towel. Right? Now the cool thing is, with our objects, we have a two-dimensional object and a three-dimensional object. Typically, two-dimensional objects are written on maybe a board, maybe the words on a page of a book. Three-dimensional objects always have a height and width and an actual thickness. There you go. There are three measurements. That makes it a three-dimensional object. Any three-dimensional object can be picked up and held in your hands. Everything. I want you to grab right now anything that's in front of you. I want you to touch the computer that you're looking at right now. I want you to touch the water bottle, the cup, the pencil, anything. Anything that you can pick up is a three-dimensional object. And all three-dimensional objects have a volume. Volume are simply those three dimensions being multiplied. So here we go. Pay attention. So here's my normal paper towel. I do have a width and a height and a certain thickness. Watch what happens. This has a certain volume. I'm not going to measure right now, but just agree with me, it has a certain volume. What happens when all of a sudden I fold it in half? Well, didn't the width decrease? Yes. It will decrease by the exact same amount as the thickness increased. So, if the width is only half of what it used to be, the thickness must be twice that. Don't you now see two layers? Yeah, it's now twice what it used to be. Has the volume changed in any way? No. That's the cool thing. I'm going to go one step further. What if I took that and folded it again in half? It's getting smaller, isn't it? Didn't this length just become smaller as well? But guess what happened to the thickness? It is that much thicker. It becomes thicker in direct proportion to how the other measurements decrease. And it has to, by logic, because it has the same volume as the original paper towel that I started with. True? True. Hang with me for one more, because this is the coolest thing of all. We have what we call a sphere. A tennis ball, golf ball, orange, basketball, things like that. They're round. And all spheres have a volume as well. We calculate it a little bit differently than we would, say, a rectangle, square object such as my paper towel. But the cool thing is this. If I took that paper towel of a known volume, which we just had, and we just agreed is the volume no matter what I did with it, guess what? Don't I now have a sphere of that exact same paper towel, and minus all the little air spaces that are in between the little things here and there that I couldn't get out? You would have to agree with me that the sphere volume is the exact same volume as the paper towel that I started with. And I'm going to prove it by opening this up. And you're going to see that even though it was a sphere and it looked completely different than how we started, it is still the exact same paper towel that I started with. That is cool, and that is math. Now you go try to do the same thing and see if you can come up with another math equation that others would be able to not guess on the first try. That's the fun of math.